Hello guys, I'm a teacher Olimboka Sijuga Masame. Welcome to Olimboka Physics. The question states that when the sun is either rising or setting and appears to be just on the horizon, it is in fact below the horizon. The explanation for this seeming paradox is that light from the sun bends slightly when entering the Earth's atmosphere. As shown, since our perception is based on the idea that light travels in straight lines, we perceive the light to be coming from an apparent position, that is an angle delta above the sun's true position. Okay, at an angle delta above the sun true positions. Underline this in your heads. Part A, make the simplifying assumptions that the atmosphere has uniform density and hence uniform index of refraction n and extends to a height h above the Earth's surface, at which point it abruptly stops, shows that the angle delta is given by delta is equal to arcsin in a square bracket refractive index times radius of the Earth divided by radius of the Earth plus height of the atmosphere minus arcsin square bracket radius of the Earth divided by radius of the Earth plus height of atmosphere, where radius r stands, which is equal to 6,378 km, is the radius of the Earth. Calculate delta using refractive index, which is equal to 1.003, and h, which is equal to 20 km. How does this compare to the angular radius of the sun, which is about 1/4 of a degree? Let us consider the diagram below. That will help us to understand the scenarios of these questions. This is the sun, and this is apparent sun, and this is the atmosphere with HH, and this is radius of the Earth from equator to the surface. Okay, and this incident rays that strike a point N and refracted it to O, and from here we will have angle delta D that we are asked to find. This is the deviation angle, which is for apparent sun, as stated here. This deviation angle above the sun's true positions, that is apparent position, that is an angle delta above the sun's true positions. Okay, above the sun true positions, this is an angle delta. This is sun true positions, and this is above the sun true positions, which is that of apparent sun formed due to extrapolated refracted rays. That we extend backwards after a refraction to form apparent image of the sun, which is bulged along the equator, along the center, and shorter along the y-axis. Okay. Consider a triangle PMN and ONM, triangle PNM and triangle OMN. Okay. From this triangle PNM, we will have incidence angle, which is equal to sum of delta plus r. Now the delta is equal to incidence minus r. And for ONM, we will have refracted r here. This refracted r is equal to opposite divided by hypotenuse for the sun. For the sine of r is equal to OM divided by NM. OM is equal to radius, and NM is equal to hypotenuse, which is radius plus height of atmosphere. We mark it with star, red star, so that we will use it later. Therefore, the r is equal to arcsin of this right terms. Okay, and this is the equation 2. From Snell's laws of refractions is expressed as you can see here. We mark this sign r with red stars because we will substitute this right terms here. Okay, now the refractive index in vacuum is equal to 1. Therefore, sine incidence is equal to refractive index for air. We substitute this sine r, then our incidence angle is equal to arcsin of refractive index times radius of the Earth divided by radius of the Earth plus h in bracket, which is equal to equation 3. Now substitute equation 2, equation 3 into equation 1. This equation 3 and this equation 2 into equation 1. Okay, we will have the expression as you can see this below. This expression is what we actually derived here. Okay, for part B, we have given the refractive index, the radius of the Earth, and the height of the atmosphere. Then we are supposed to find the delta. The delta now is equal to 0.2 degree. Now we are asked to compare this delta of apparent sun to delta of the real sun, and which we have given as a quarter. Okay, we compare it by using a percentage loss, by taking the real angular radius of the sun minus a apparent angular radius of the sun, and we from this we find the percentage loss of original sun angular radius compared to the apparent one. By finding the percentage loss, we will have the expression like this one, and from these expressions we will substitute the delta, we will substitute, and we will have a 20%. We will have 20%. Okay, we just take this in left and this take this in right. This become positive and this become negative. This is what I wrote here, and this is 0.2 degrees. As you know, this angular is equal to 0.2 degrees, and this one is quarter, which is equal to 0.25 degrees. Okay, and here we will have apparent sun is 20% less to that of the original sun. Or we say that apparent sun will use almost 80% of the original radius of the sun to be appear at this position. Okay, thanks for watching. Please like, share, comment. Don't forget to subscribe to this YouTube channel for more videos like this one. Thank you.